Determine the value of the limit, as n tends to infinity, of 2n plus 1 over 5 minus n, and use the formal definition of the limit to prove that this value is correct. Alright, so as n gets really big, the 2n on top is going to be what's most important. It's going to grow faster than 1, which never grows. Similarly, the minus n on the bottom is going to be what matters in the long run. So eventually this is going to look like 2n over minus n, approximately. And so I should expect the n's to cancel out, and the limit, I'm going to guess, is minus 2. Okay, that is going to be the limit, but now we actually have to prove it. Okay, so what would we say? Well, I would say I claim that the limit as n tends to infinity of this particular sequence is minus 2. Okay. Now to use the formal definition, well, let's recall it. What do we need to do? For any epsilon greater than 0, we must find an n based on that epsilon. Okay, different epsilons require different n's. So that if our input, our index, is past this n, then the difference between our sequence and our proposed limit is less than epsilon. Alright, so we will start with some arbitrary epsilon, but this is the condition we need to prove. What sort of n's would satisfy that? Okay, what sort of n's would imply this? Well, let's play around with the end result. And this is just rough work. Okay. The minus minus we can simplify to a plus. I suppose we could get a common denominator here. Let's see, plus 2 times 5 minus n, so that's going to be 10 minus 2n over 5 minus n. But now we can combine them. The two n's will cancel out. We'll have 1 plus 10, so 11 over 5 minus n. And, well, absolute value distributes over multiplications and divisions. So it's absolute value of 11, which I'm just going to write as 11, over the absolute value of 5 minus n. And for n bigger than 5, which it will be if it's heading towards infinity, the 5 minus n is negative, so we do need the absolute values there. But we need to show that this is less than epsilon, because this is just a really simple way of writing what we're looking for. Okay, so let's play around with this a bit more. Okay, if we rearrange it, divide both sides by epsilon, which is positive. Right? Epsilon is positive, so the sign here doesn't change. Multiply both sides by the absolute value of 5 minus n, also positive, so the sign doesn't change here. Okay. Now, if we make an assumption for values of n that are greater than 5, 5 minus n is going to be negative, so the absolute value of 5 minus n is just going to be n minus 5. Now, 5 minus 6 is negative 1. In absolute value is 1, which is the same as 6 minus 5. Okay. So if that's the case, if we make that assumption, then we can get something like this. Now, we are going to have to incorporate this into our choice, so we might have to write something like n is the maximum of 5 and whatever else we're working with. Okay, just planning ahead. We might need something like that. Okay, add 5 to both sides. Get rid of the minus 5. Okay. And this looks an awful lot like something based on epsilon. Different epsilons lead to different n's. Okay. Is less than our little n, which is exactly the sort of thing we need to start off with. Okay. Furthermore, notice that since epsilon is greater than 0, 11 over epsilon is also going to be greater than 0. Positive over positive is still positive. Okay. And so this n here, which I'm going to declare to be 11 over epsilon plus 5, is greater than 5. And so if n is greater than capital N, then n is greater than 5, and we won't need to worry. Okay? But now we write up our formal proof. Okay? So let epsilon be greater than 0, okay? And it's just going to be arbitrary. Okay? We're not going to show that this is true for epsilon equals 1 or 1/2 or something like that. Okay? We're just going to let epsilon be some real number and show that we can work this out. Okay? We claim capital N being 11 over epsilon plus 5 will work. Okay, now we make our assumption. Suppose that we're dealing with an index greater than n. Now we need to do a whole bunch of math and end with our desired statement. Okay, just from this start. Now we know what the epsilon, we know what n is based on epsilon. It's 11 over epsilon plus 5. Okay. So what are we going to do here? And quite often it helps to try and reverse our rough work. Okay. It doesn't always work, which is why I encourage people when they do formal write-ups, don't just start here, work backwards, and declare, oh, that's a good n, that must be it, proof over. No, no, no. You actually have to start with the, here's an epsilon, here's an n, make this assumption and show that it works. Because sometimes reversing your rough work will make you realize, oh, I need to assume something else. Oh, I haven't accounted for this being positive. I need to make my n a maximum of a few values. Okay? So you got to actually do it in the right order. All right, so suppose we've got that. Let's say something to the effect of then n minus 5. So I am just trying to reduce, reverse the rough work we did. Okay, so we can see that now. Since epsilon is greater than 0, 11 over epsilon is greater than 0. So our n value is greater than 5, and thus n, little n, our index, is greater than 5. So 5 minus n is negative. And we see the absolute value of 5 minus n is n minus 5. Okay, so I can take this n minus 5 here and replace it with the absolute value. Right, because we need it to be 5 minus n for more of our work. Okay, slowly we just multiply both sides by epsilon. If you want to, make a comment like epsilon is positive, explaining that the sign isn't going to change. Okay, you can make a similar comment that absolute value of 5 minus n is positive, so the sign isn't changing. Okay, and now this was just our fancy way of writing our conclusion, so we just expand it out. So epsilon is greater than 11 over 5 minus n in absolute value. Okay, so we'll write this as 2n plus 1 plus 10 minus 2n. n plus 1 over 5 minus n plus 2. And at long last, we do the minus negative 2. And we put the little box to tell everyone, hey, we're done. Okay? Or we could say, this is what we wanted, as desired, that sort of thing. Okay? But notice once again, we didn't get to control what epsilon was. This will work regardless. Pick epsilon equals 1, you'll find your n. Pick epsilon equals 10, you'll find your n. 1/10, 1/10,000,000th, you'll still be able to find an n, and this will all work. Okay? We don't control the epsilon, we do control the n. And the only thing we assume is, suppose the index of our sequence is past this n, okay, and we used nothing else, and we made it all the way through and showed our conclusion. That the values of our sequence are close enough to negative 2. They are within epsilon of -2. So there, formal definition of the limit, proof that the limit here is, in fact, -2. Okay? And, some people look at something like this and say, oh, well, that flowed very nicely. Well, thank you. I've practiced these sorts of things. But you can easily forget that the -2 was important. Okay? If it had been something like -3, you would have had +3. You would have had, the ends wouldn't have even canceled out up here. You would have had something very different. Okay? So it's easy to forget. We had to find the right limit. Okay? You can't do this epsilon n stuff with any other number. It had to be -2. And, I would encourage you, if you're a little unsure about epsilon n's, to try and prove that -3 would have been the limit. It just won't work for you.